is rate of change? So we did a couple practice problems. First thing we're going to talk about is instantaneous rate of change, which we've talked about before. But now we're going to do a couple problems with just one here, and then you're going to have some homework problems that deal with it in context. Okay, what it actually means in context. And then we will talk about motion along a line. So that position, velocity, acceleration, how those are all connected. Okay. And why? Well, derivatives give the rates at which things change in the world. All right. Calculus has a lot of real world implications. We get into it a little bit, but we don't get into everything you can do. Okay. That's why if you went into like an engineering, you would take 3 or 4 calculus classes, because engineering is all hands-on, real world type problems. Okay. So we are getting into the baseline, getting that calculus 1 experience. If you go into engineering, then you're going to take more and more calculus. If you're not going to engineering, there's still applications of calculus in other contexts. All right, so let's jump right into an example. There's no new rules or anything that we're going to cover today. It's actually applying what we know. We had this set up. The area of a circle is a function of the radius, is A equaling pi r squared. It's nothing new, nothing you haven't seen before. Yeah, area of a circle is pi r squared. But I want to highlight the notation on this slide as well. A function of the radius. So that means r is the independent variable. I can choose whatever I want for r, and that will tell me what the area is. Okay, so if r was 2, r was 5, r was 1,000, I could give you the area. Okay, if you told me the area, I can work backwards and find r. But in this notation, the area of a circle is a function of the radius, is A equals pi r squared. All right, find the instantaneous rate of change of the area A with respect to the radius. Instantaneous, whenever you see that word instantaneous, and I've underlined it, that means that you need to find the derivative. Okay, instantaneous is the slope of the tangent line at a specific point, at an instant. Okay, instantaneous, we need to find the derivative. Find the instantaneous rate of change. So the rate of change, how is it changing? What's the rate, in this case, that my area is changing with respect to the radius? So notation, we can write this as dA dr. So that's that notation, dA dr, rate of change of my area with respect to radius. We could also see this written as A prime of r. So those mean the same thing. But again, I'm going to show you the two notations often because those get used interchangeably, and I want you to be comfortable with both kinds. So this is simply asking for the derivative. So what is the derivative of pi r squared? What is it? 2 pi r. All right, so the derivative function is 2 pi r. It was asked last class because circumference is 2 pi r. This has nothing to do with circumference. Okay, this is the derivative function. Okay, so don't get this confused that you're getting another value that's, okay, nope, we're trying to find the instantaneous rate of change of our area with respect to r. Okay, so that becomes 2 pi r. Evaluate the rate of change of A when r equals 4. All right, so notation-wise, we could see it written like this, dA dr, with that big vertical bar, r equaling 4. That's exactly what it's saying. Okay, rate of change of A when r equals 4. Or we could see it written as A prime of 4. Either way means the exact same thing. So if I were to evaluate, I would get 2 pi times 4, and so I'd end up with 8 pi. This again is the instantaneous rate of change. And what this means, so we have, maybe think of a disk, a circle, whatever, however you want to think about it. Okay? My disk is getting bigger. And exactly when my radius is 4, the rate of change, how much it's changing, is 8 pi. So the rate of change is 8 pi. So again, this is the rate of change at the time when r equals 4 is 8 pi. Okay? That is not saying that the area is 8 pi. How much it's changing is 8 pi. Okay, because the actual area, if I put the area back in, r squared, 4 squared to be 16. The actual area of the disk would be 16 pi. What we're finding is the rate of change. Okay, how fast it's changing. It's changing at a rate of 8 pi. Okay, so that's why it's a little bit different. All right, let's get into actually some physics stuff now. Motion along a line. Okay, position. So we're going to deal now position as a function of time. Position you will see denoted with the letter S most often. Okay, they could say S, they could say S of t, because remember it's a function of time. So time is my independent variable. If I give a time, I know what my output's going to be. Could see it as F of t. You may also see it as X of t. Again, calculus, they like to change it up variables, but they all mean the same thing. And a lot of it is just understanding exactly what it means. So S you'll see most often. If you see a function S of t, there'll be some context with it that you'll know it's something about a line, motion along a line, something with that. So if you see S, that represents position. Okay? So we thought about it on a coordinate axis. My time is my independent variable, and my output is that S of t. Okay? So if I had some curve going on, and I was here at 5, maybe up here at 8, if I go out to 10, and I'm up here at 12 or something like that. Position is a spot. Like if I walked 5 meters and stuck a stake in the ground, my position would be 5 meters from wherever I started at. Okay, it's simply a spot. Okay, it's where that position lies. Okay, displacement now. Displacement represents the change in position. Okay, so if I wanted to find the change in position, say I started 2 meters already away from something, and I walk another 6 meters, okay, well, 8 meters essentially from where I started, but I've only displaced by 6 meters, okay? So we could think of this as my change in y values, okay? So here to here, this is my displacement. It's pretty messy. All right, we could think of that as y2 minus y1 if we actually think of it as coordinates. Okay, so that f of t plus delta t minus f of t, all that stuff, all that's saying is my y2 minus y1 values. Okay, so we're going to start with position. Now, motion along a line. Now we're going to actually talk about movement. Okay, position, there was no movement. Okay, I'm standing there, stake in the ground. I'm 5 meters away or something like that. Okay, I'm stopped. There's no movement going on. If I get into movement, now we're talking about velocity. So velocity is movement. And velocity is that change in position, my displacement, now divided by time. So now I can think of it as, okay, how far did I move? How long did it take me to move? Okay. Now we can start to think of this for average velocity. And we've talked about average before. Remember, average is not instantaneous. Average velocity is the slope of the secant line. And my things were out of order, so I'm going to jump ahead. Okay, so again, on this graph, if I was here at 5, and I'm here at 8, and here at 10, and 12, my slope of my secant line, that is the average velocity. Okay, do not make that mistake. Average simply is that slope of the secant line. Connect your 2 points, find your slope, like you've done since 6th grade probably, if not sooner. Now let's talk about units. So units on velocity would be something like meters per second. So my displacement, number of meters that I've moved, and then how long it took me to move that number of meters. So meters per second is what I could have for velocity. Now we can talk instantaneous velocity. So again, do not get those bumped together that they're the same. Average and instantaneous are not the same. Average is the slope of that secant line. Instantaneous is at a specific point. Okay? And we can find instantaneous velocity by finding the first derivative of position. So if I'm given a position function, I could find the first derivative of it, and that will give me my velocity function. So s prime of t equals vt, and ds dt also equals vt. Okay, mean the same thing, just different notation. So instantaneous velocity, if I were to look at this, I could say, okay, if I want to find it here at this point right here, I'm going to have my, oh, that's not very straight, but I'm going to have now right there at that point. It's only going to touch at one point. So that's my instantaneous velocity. So it's a different slope to that tangent line. Speed is the absolute value of velocity. Okay, speed has no direction. Okay, so that's why we just do it as absolute value. Speed will always be positive. So if we find the velocity function, we can take the absolute value of it, and that will tell us speed. Okay, so absolute value of v of t, same thing as absolute value of ds dt. Okay, speed will always be positive. Let's take a look at a second example. A projectile is shot upward from the surface of the Earth, reaches a height of s equaling negative 4.9 t squared plus 120 t meters after t seconds. Okay, So this is a position function because it's s. So if I were to put a time in there, so I said after 5 seconds, it would tell me the height in meters. After 25 seconds, it would tell me the height in meters. Okay? It's just a position. It's a single spot. It's a point. So from this position function, what is velocity? Or what is the velocity function? Negative 9.8 t plus 120. Okay, that is the velocity function because that is the first derivative of position.
Excuse the interruption, this is the last time. All students that have not had their picture taken and or need retake, report to the Commons at this time. All students who have not had their picture retakes done or still need their picture taken, report to the Commons.
Okay, so now that we have a velocity function, now we can actually find the velocity after 5 seconds. So v of 5 would be negative 9.8 times 5 plus 120. And when I do all this, I end up with 71. What will be my units on 71? Meters per second. And this is important. If you do not put proper units on there, I'm going to take points away. Okay, so you need to make sure that you understand the units, what's going on with this. Again, position function, that would just, my units on that would just be meters. But velocity now, it's meters per second. All right, higher order derivatives. So I have in here, what does it mean to find the derivative of a derivative? Okay, so if I had some function going on, say it was something that looked something like that. Okay, if this was my original function, well, let's call this f of x. Well, then my derivative function is going to represent the slope of that. And so I have 1, 2, 3, 4, 5 spots where it's 0. So 1, 2, 3, 4, 5 spots where it's 0. And it's negative, then positive, then negative, then positive, negative, then positive. It looks something like that. Okay? But now I could find the second derivative of that, which would represent the slope here. Well, now I only have 1, 2, 3, 4 zeros. So I'm going to have 1 here, 1 here, 1 here, and 1 here. And then I have a positive slope on this first leg, so it's actually up here. And then it's going to look something like that. Okay? And then I could keep going. Okay? So the derivative of a derivative simply means that I'm looking at those slopes. Okay? So say we have an actual function of 4x cubed. 4x cubed, what is the first derivative? Well, let's just start with that. So 4x cubed is going to look like that. It's going to be that nice S shape. What is the derivative of 4x cubed? 12x squared. If I were to graph 12x squared, it'd be this nice parabola, okay? Which I can see that on my 4x cubed, it had a positive slope, 0, positive slope again. So this above the x-axis means positive. So it's positive, 0, and then stayed positive. What is the derivative of 12x squared? 24x. So if I were to graph this, come on, there we go. This one is going to be actually a straight line, okay? But it means this has a negative slope, 0, positive slope. So it's below the x-axis, 0, above the x-axis. what is the third derivative going to be? Just 24. 24, sorry, I'm getting bunched up. Forgot I had one more slide there. So 24 is just going to be a horizontal line. Y equals 24 is a horizontal line through 24. What's the derivative of 24? 0. You can't graph that. Okay, so the slope of that horizontal line would be 0. We're done. So higher order derivatives, you can continue taking the derivative or finding the derivative until you reach 0. Once you reach 0, there's nothing else you can do. Okay? And you should see on each of these that my degree is changing every single time. Every derivative becomes one less degree. Okay, so the one that I showed with all those humps there in the top right, okay, every single time I was getting less and less peaks and valleys. All right, so we talked position, we talked velocity. Now, the last thing we're going to talk about is acceleration. Instantaneous acceleration is the derivative of velocity. So we can think of a of t for acceleration is the first derivative of velocity, and we can think of that as the second derivative of position. So s double prime of t is the same thing as a of t. Now here I say be careful with the units. All right, so we know position is just our change in s, which is in meters. Velocity is the change in s divided by time. And so we end up with some meters per second. Acceleration is going to be now the change in velocity all over the change in time. My velocity, I know, is meters per second in terms of units, and my time is in seconds. So my actual units will be meters per second per second. Or we can write it as meters per second squared. Okay? So meters per second is the units that we'd have on acceleration, assuming we are in meters and seconds. If we were in feet and hours, then it'd be feet per hours squared. My AP Physics students, do you know the change in acceleration, what that unit is called? Close. You got it, Jacob? Jerk. Yep. So the change in acceleration with respect to time is called a jerk. And so it'd be meters per second per second per second, or meters per second cubed. And I don't know the one after that. You know the one after that, Jacob? Or no? Jounce. I think so, yep. You'd have to ask Mr. Reinhardt. No, this is as far as I go. All right, so let's take a few minutes here to look at a few slides to represent movements. Oh, did you need that slide back up, Cassidy? You're fine. Okay, like 4. But it's all this one problem. It's a visual problem. You just look at it and you can tell me the answers. Okay, so particle movements. So movement, that's important. Okay, it's moving. So they'll give us a graph that this is a velocity versus time graph. Pay attention to the axes that they give you. Okay, if they give you a graph, look, is it velocity? Is it acceleration? Is it position? Because they could give you any of those 3 types of graphs and then ask you questions about something that's not even on the graph. Okay? If they give you a position graph, they could say, well, what's the velocity? Well, I could say, well, I know it's the slope of this position line, so that's actually going to be my value. Or they could give you the acceleration graph, and we'll get to this later, and they could ask you questions about velocity on it. Okay, so pay attention to what graph they give you, what the axes are labeled. Okay, so this is the velocity graph. So talking movement, velocity is movement. Again, position, you're not moving. That's put a stake in the ground, you're standing there, that's your position. Okay, but now we're moving. When does the particle move forward? So what can I say about my velocity if I'm moving forward? What? Positive. Okay, v of t is positive. Okay, and in this case, we could say above the x-axis. That's when the velocity is positive. So it says, when does it move forward? I would have from 0 all the way to 2, in this case, time is in hours. So from 0 to 2 hours, it's moving forward. Okay, and it's 2 non-inclusive because at 2, it's neither moving forward or backward. Okay, it's right on the x-axis. So it only moves forward on the interval from 0 to 2. Okay, do not get thrown off that it shows from P to Q that it's going down and think that it's moving backwards. It's not. It's still above the x-axis. Okay, moving backwards is when our velocity is negative. And so we can think of that as below the x-axis. Okay, and this one, it's only from 2.5 all the way to 3.5. When does the particle speed up? What's the relationship between speed and velocity again? Louder, Kelsey. So, correct. So what could you say about speed then? What I'm trying. So absolute value of velocity is speed. Okay. So when does the particle speed up? So what we're thinking about now is moving away from the t-axis. Oh, it should be all t's, not x. Okay, so this chunk right here, it's speeding up. But also, this chunk right here is speeding up. Okay, it doesn't matter that it's going backwards, or we say backwards, often we'll say left, forwards we'll say right. Okay, so when does the particle speed up? It's on this interval from 0 to 1, and on the interval from 2.5 to 3. So there's 2 intervals where this was speeding up. When does it slow down? Well, it's going to slow down when it's getting closer to the x-axis. So in this one is the only spot. Okay, we don't know what happens after 3.5. Our trial ended. So the only time it's slowing down is between 1.5 and 2. So
Why did you include backwards where it's like a flat 5?
no, I didn't. So moving backwards is 2.5 to 3.5. So it's from here. So 2.5 to 3.5.
So why is it where it's flat there, but then
Because it's still moving. If we had on the vertical axis, maybe -5, it's still moving, it's just maintaining a -5 velocity.
Oh,
So it's going -1, -2, -3, -4, -5. It's maintaining -5 as time progresses. Yep. Good question though. So again, understanding which graph they give you, velocity graph means it's moving this whole time except for one section time, which we'll get into. Okay, acceleration. So now they give us our velocity graph. This is the same graph, but now they're asking us a question about acceleration. So the acceleration is positive. We know acceleration is the first derivative of velocity. And so we want to know where this is positive. Okay, meaning slope. So the only area that's positive is on that chunk right there. That's the only section where I have a positive slope, and so I have a positive acceleration. Okay, so from 0 to 1. So now we're looking at the slope of these lines when we're talking acceleration, not the actual values. Acceleration is negative, so when is my slope negative? Okay, on this interval here, I have a negative slope, and then also on this interval here, I have a negative slope. Okay, it doesn't matter that it crossed that t-axis, it has a negative slope. And so from 1.5 to 2, and from 2.5 to 3. Acceleration 0. So that's going to be whenever my first derivative, whenever my slope is 0. So the only time this is 0 is on this section right there, but also up here too. So this is 0 from 1 to 1.5, 2 to 2.5, and 3 to 3.5. Okay, so acceleration is 0. It means the slope of my line is 0, and that's going to occur in 3 spots. When does the particle move at its greatest speed? So again, speed is the absolute value of velocity. So I'm looking for the greatest velocity, but its absolute value, so the greatest velocity could occur above the t-axis or it could occur below the t-axis. Okay? We're going to go ahead and say that these values are the same distance away. Say it was like a -5 and a +5 or whatever. Okay? It's not labeled, but we're going to go ahead and assume that these are the same. Okay? So its greatest speed occurs from 1 to 1.5, but also from 3 to 3.5. Say it's going 5 kilometers per hour to the right on the 1 to 1.5, 5 kilometers per hour to the left from 3 to 3.5. So we'll say the speed is the same on that. Okay, last slide. When does the particle stand still for more than an instant? Okay, so standing still, we're talking velocity now. Okay, we're not talking the change in velocity. We're actually looking at the velocity. Here above the t-axis, it was moving to the right. Below the t-axis, it's moving to the left. So this is the only interval where it's not moving left or right. It's stopped. It's standing still. Okay, so 2 to 2.5. And then when did it reverse direction? Simply stopping does not indicate reversing of direction. It actually has to cross through the t-axis. This one, it does not cross through until 2.5. Because if at 2.5 it went back up, it was going right, stopped. If it went back up, it means it's going to go right again. It never changed direction. It has to cross through that t-axis. Okay, so there's a whole lot of questions that can be asked given one graph in terms of velocity, acceleration, potentially position if they give you a position graph. There's a whole lot that can come from it. Okay, so 3.4 is in Math Excel, due Wednesday by midnight, but I will give time tomorrow in class to work on this one a little bit more.